The upgraded VLA has been in full operation for about a year now. From the air, it looks just like the old VLA. It's the same 27 telescopes in the same positions on the ground. The difference is all in the electronics. The electronics were replaced end to end. The receivers on the VLA were replaced. The old ones had their frequency range expanded, and new receivers were inserted as needed to fill the gaps. The new correlator is able to process signals from a bandwidth that's about 100 times as great as the bandwidth that could be processed with the old correlator. The resulting sensitivity improvement is about a factor of 10. So that without making the telescopes any bigger, we've been able to make the sensitivity a factor of 10 larger. It's as if we could have turned our 25-meter telescopes into 80-meter telescopes in terms of sensitivity. We have been able to make new images of radio sources with the improvements that I described before. Some of the examples include the radio galaxy Hercules A. This is a radio galaxy that's powered by a supermassive black hole in the center of a distant elliptical galaxy. The black hole in the center of that galaxy weighs on the order of 1 billion times the mass of the Sun. And the energy source for the radio emission is material falling into that black hole. As that material releases its gravitational energy, it accelerates electrons in the vicinity to nearly the speed of light. And those electrons in the magnetic field around the black hole emit what's called synchrotron radiation. What you see in the image of Hercules A is that synchrotron radiation. The relativistic electrons are shot out in high-speed jets along the directions of the rotation poles, the north and south pole, as it were, of the supermassive black hole. So what you see is a bright source located at the black hole, and then two jets coming out in opposite directions, narrow beams of relativistic electrons that are moving at nearly the speed of light. The whole beam of electrons is moving so fast near the black hole that relativistic effects actually make it invisible. And so you'll notice that between the central black hole and the visible jets, there are gaps on either side. Eventually, the blobs of electrons in the jet slow down enough that you can see the jet again, but they're still moving at very high speeds. So, like a drill, they bore their way through the surrounding gas and remain in narrow jet for a long time. For so long, in fact, that they bore their way entirely out of the galaxy, which is much smaller than the radio source and is visible as a glow centered on the central black hole. They go out to a distance that's many times the size of the galaxy before finally encountering so much ambient material that the momentum loss from just crashing into the ambient material stops them, much like what happens to a bullet if you fire it into a pile of mud. At that point, the electrons individually are moving at nearly the speed of light, but not coherently. They're moving randomly. And so the radio source diffuses out into the large blobs or lobes that you see at the end of the radio source. And there's a huge amount of structure visible in those lobes. You can see wisps and curls and so on that depend on the past history of the electrons being ejected from the galaxy. Sometimes they're ejected in bursts, sometimes continuously, and the material that the electrons encounter along the way. If you see a bright spot along the jet, that's a place where the electrons have encountered a lot of ambient material. They're slowed down, they're compressed along with the magnetic fields, and you see a glow of very bright emission. The new VLA is able to make a much better image of radio galaxies like this than the old VLA, This is the best image of Herc-A that's ever been made. And one of the reasons that it's the best image is that the VLA can be configured into 4 arrays at different times, starting from the smallest that was about 0.6 of a mile across, going to a somewhat larger array that's about 2 miles across, one that's about 5 miles across, and then finally the one that's about 20 miles across. Each array has its own strengths. The small arrays don't have high resolving power, but they're very sensitive to extended or diffuse emission, such as the emission in the lobes, and define that emission very well. The larger arrays are not sensitive to the extended emission, but are very sensitive to fine-scale emission, tiny point-like sources or very narrow jets. In a computer, we can combine all of the information from all of those images to make one single image that's as good as if we had all of the arrays operating at the same time. And that is why this image contains both fine details and very extended structure down to very low sensitivity levels. We really see all of the radio emission from this source at once.